Okay, let's dive into this. Welcome to this explainer. Today, we're taking a massive leap from the chalkboard directly into the real world. We've combed through literally towering stacks of academic AI papers from the year 2026, and our goal is to translate all that incredibly dense, groundbreaking theory into something way more tangible. We're talking real-world, everyday applications. We're going to look at exactly how this high-level math is actively changing the world around us right now.
So, here is our roadmap to get us there. We've got Section 1, AI's real-world leap. Then, Section 2, healing through machine learning. Moving into Section 3, robots that learn and adapt. Section 4 covers smarter, faster content creation. And finally, Section 5, fairness and lifelong memory.
Starting off with Section 1, AI's real-world leap, breaking out of the lab.
Think of this explainer as a day in the future that has, well, suddenly become our present. And hey, I want to reassure you right up front, we are absolutely filtering out the incredibly dense mathematical formulas today. Instead, we're applying a highly practical lens focused entirely on how these processes actually benefit humans. For a long time, the most sophisticated algorithms were totally confined to strictly controlled laboratory settings. But what the latest research shows us is that highly theoretical algorithms are actively breaking out. They're becoming practical, reliable tools that you and I will interact with every single day. To show you this, we have distilled the absolute cutting edge of applied processes from 7 highly technical 2026 machine learning conferences. We're pulling from gatherings focused on parsimony, causality, lifelong learning, dynamics and control, and even geometric topology, all to show you exactly how this math impacts reality.
Now, what's really interesting about this next section, Section 2, healing through machine learning, is how math is actively saving lives in the clinic. It is right here that abstract math is literally saving lives. Let's start with causal machine learning. So this is an AI approach that goes far beyond just noticing that two things tend to happen at the same time. It actually determines real cause and effect relationships. Picture a doctor sitting in a super busy clinic. Using causal ML as a diagnostic assistant, they aren't just looking at a list of symptoms. They are running algorithms that analyze complex pharmacovigilance signals in electronic health records. By doing this, the doctor can pinpoint the exact cause of a severe issue, like say, drug-induced acute kidney injury, way before it escalates. It's not just a guess based on patterns, it's a mathematically backed deduction of cause.
Traditionally, we relied on static medical imaging, right? Taking a picture and just hoping you spot the problem. But now, utilizing research from the 2026 Conference on Causal Learning and Reasoning, we have counterfactual chest X-ray generation. By using causal and active learning, the AI can essentially show a doctor what-if scenarios. What would this specific lung disease look like if the patient hadn't smoked? Or what if the intervention was applied earlier? This directly and dynamically supports clinical decision-making on the fly.
And the healing applications just keep going. Pulling from the parsimony and geometry conferences, we're seeing 3 more massive leaps. First up, deployable seizure detection. By using highly lightweight models, this life-saving monitoring can happen on everyday low-power devices. Second, we're seeing the classification of complex histopathology slides using a concept called persistent homology. That's basically finding the hidden, unchangeable shapes within cellular structures to diagnose disease. And third, researchers are literally mapping interbrain networks via geometric topology to better understand how humans connect. Every single one of these complex theories is anchored right back to efficient, effective patient care.
It's incredible to see on a screen in a clinic for sure. But what happens when these algorithms leave the screen entirely and enter the physical, highly unpredictable world we live in?
That brings us to Section 3, robots that learn and adapt, moving safely in our world.
Tapping into some fascinating research from the 8th Annual Learning for Dynamics and Control Conference, the entire focus here is how algorithms allow machines to safely interact with entirely unpredictable physical environments. A massive part of this safety relies on what are called control barrier functions. You can think of these as mathematical safety filters. They act as invisible, real-time guardrails for dynamic systems. To put this into a physical context, imagine a walking robot navigating a busy city sidewalk. There are hard-to-model physical constraints everywhere: uneven pavement, sudden gusts of wind, unpredictable pedestrians walking by. These latent control barrier functions run in the background, smoothly filtering the robot's planned movements to ensure it never crashes into a human, no matter what surprises the physical world throws its way.
So, how does a robot actually learn to live alongside us? Well, it's a step-by-step process of lifelong deployment. Step 1 is deploying a single-life robot in a brand new environment. It doesn't get to run a million simulations first in a lab. Step 2, the robot must modulate its behavior on the go, adapting based entirely on immediate real-world feedback. And Step 3 is truly fascinating. Based on the Lifelong Learning Agents Conference, there's a framework called SECURE, which stands for Semantics-Aware Embodied Conversation Under Unawareness. Basically, it allows the robot to maintain a safe, embodied conversation and interaction with you, even when it's totally unaware of certain aspects of its environment. It safely adapts without ever needing a full system reset.
Section 4. Smarter, faster content creation. Efficient generative AI.
Now let's shift our focus from the physical constraints of robotics to the absolutely boundless world of the creative industry. To see how the Parsimony and Learning Conference is radically democratizing video and audio editing, we can look at a new paper titled Enhancing Low-Cost Video Editing with Lightweight Adapters. And this brilliantly illustrates how that technical jargon actually translates to faster, vastly cheaper AI video generation that you can run right on your everyday laptop. The researchers use a process called temporal aware inversion. All you really need to know is that this complex math simply means high-end, Hollywood-level content creation is becoming accessible to absolutely everyone, regardless of their budget.
You can quickly see why this is such a huge game changer. State-of-the-art deep learning architectures traditionally require massive computing power, like entire server farms. But new Parsimony models use techniques like pruning and quantization, which is essentially trimming the fat and compressing the data. As a result, the computing power required literally drops off a cliff. Doing more with less makes advanced AI deployable for everyday creators right in their living rooms.
And we see this applied brilliantly in audio editing as well. Let's walk through this process. Step 1. Let's say you identify a pronunciation error in an AI-generated audio track. Normally, fixing a core mistake in an AI model requires retraining the entire massive system from scratch. But Step 2 uses a new process called SonoEdit, utilizing something called null-space constrained knowledge editing, which leads to Step 3. You seamlessly correct that specific audio output error locally, instantly, and without retraining the overarching model. It saves massive amounts of time and incredible amounts of computing cost. But all this incredible capability, diagnosing diseases, walking safely among us, generating instant video, it raises a really vital question. How do we ensure these highly efficient, capable models remain fair to everyone? And how do we ensure they don't forget what they've learned as they age?
Section 5. Fairness and lifelong memory. Building trustworthy AI. So, the crucial point is,
if AI is going to be truly integrated into our lives, building trustworthy, unbiased, and continually adapting AI systems isn't just a fun bonus feature, it is the foundational requirement. From the AAAI workshop on bias in multimodal AI, researchers are deeply auditing how human-driven biases basically sneak into the math. They impartially detail 3 key areas of focus. First, annotator risk preference, understanding how the personal risk tolerance of the humans who label the data causes systemic bias in the AI's output. Second, auditing cultural representation bias inside large language models to ensure global fairness. And third, analyzing alignment divergence in multimodal AI, basically checking if the AI's actions actually align with the diverse values of the humans using it. We literally have to audit the machine to fix the human bias hidden inside it.
And to be truly trustworthy, an AI needs to be able to learn over time without breaking. This is continual learning, a major focus of the Lifelong Learning Agents Conference. It's the process by which an AI learns new tasks on the fly, out in the real world, without suffering from what researchers call catastrophic forgetting, which is where learning a new skill completely overwrites its past data. We're actively designing AI to mimic ongoing, human-like adaptation.
let's move to this comparison and see how this builds. We can contrast this directly. Old, static AI models freeze after their initial training. They are brittle and highly vulnerable to things like data poisoning. But the new reality is lifelong learning agents. These systems continuously adapt. They preserve their plasticity, their ability to bend and mold, in the real world, which makes them resilient and helps them mitigate bad data naturally over time.
Which leaves us with this final thought. We've seen these algorithms leave the theoretical lab. They are now actively editing our videos, healing our bodies in clinics, and walking safely alongside us on the sidewalk. The question is, as we move forward, are we merely building tools that just calculate equations? Or are we truly building systems that will continuously evolve right alongside us? It's a fascinating future, and the math is already making it a reality. Thanks for joining me on this explainer, and keep learning.